Okay, so hello everyone. Thanks for being here. And I'm Yanping from Loyola Marymount University. I will talk about engage students with hands-on activities on the first day of a DE class. So I want to clarify a little bit. I want to talk about using similar materials to teach differential equation with the modeling first approach. I do want to mention, and just like Lee Zhang mentioned earlier, I was in the same workshop like her, like 1.5 years ago, and I learned about this activity from that workshop, and I was like, it blows up my mind, and I was super excited about it. So I modified a little bit, implemented in my class. It's the first day of my differential equation class. I skipped introduction of the syllabus and everything. And so the DE part here wouldn't be too complicated. I also, before I move on, I want to also invite everybody to consider joining our breakout session later today. We're gonna chat a little bit about using ChatGPT in the classroom. So maybe you have something to share, maybe you want to hear what others have to say, but that's just a quick start. So I'm from Loyola Marymount University. We are in Los Angeles. We are 5 minutes away from Los Angeles airport. So if you are around the neighborhood, feel free to shoot me an email. Maybe you want to come and present a little bit. We have a small math department. We have very diverse students body, and we belong to the School of Science and Engineering. So the differential equation course, I'm currently teaching out of like 50 students, 2 sections, which is a total of 50 students. I think I got 2 math majors. The rest are pretty much all engineering students. So just want to let you know what the class is like. And I personally do a lot of differential equation model for my research. I'm a biomathematician by training. So I've used differential equation in a lot of projects I've done before. So I support modeling. I think that's super powerful and I'm a big fan of it. Well, some of the common concerns I've heard and I've discussed with my colleagues, you probably all know that. So one question I had from my students is that what exactly does differential equation do? And I've chatted with my colleagues a lot of times, and sometimes I hear frustration about, I don't really use separable equation or integrated factor in my own research. Like, why do we want to teach students that? Well, I share the same concern and struggle from time to time. And there are also publications about concerns from students, struggles from students about DE are complex issues. Students may find it difficult to understand. The students who are quite successful in algebraic solutions indeed did not fully understand the related concept. So it's a mixed bag of challenges. So for me, I gradually, after I joined the Mindy workshop organized by Simeo, so I gradually changed my way of teaching. I focus more on modeling and numerical simulations. And I think the idea of modeling the classroom is super important. It would, starting with real world problems, you can see the relevance of mathematical concepts they are learning and understand how they can be applied to practical situations. So it improves their real life understanding of the applications, and modeling provide a context for the mathematical concept being taught. So it helps students to understand and retain the materials better. When I say student ask me, what exactly does differential equation do? He was taking a DE class with another professor, and it was 2 months into the semester, and he had no clue what exactly he was trying to do. Well, modeling problems require students to analyze data, make assumptions, apply mathematical concepts to find a solution. So it's not pretty. It's not those math problems we usually feed them. We don't have pretty data anymore. We don't have those made up data anymore. So it would actually develop students' critical thinking and problem solving skills. And all models are wrong. We've all heard about it, and but some are useful. So modeling problems also allow students to consider different approaches and try to find solutions. It encourages them to be creative and innovation in their problem solving skills. And of course, the last part, which is super important, we all talk about active learning nowadays. So modeling problem often involve the real world data, open-ended questions, which can engage students more compared to the traditional abstract mathematical problem solving. So again, we want to model it. We want to model it early, and we want to solve problems numerically. So that's the big idea I learned from the Simeo study workshop. So this is what exactly I did. It's slightly modified, and I do find some issues. So when I implement it, so I keep modifying it. Well, I build everything on top of the spread, the common code material. So the material, what we need is pretty easy. We need a cup, we need beans of different colors. I didn't use but that's also a good choice, of course. And we need a map. I use our campus map, and I bring students to computer labs. So we have 3 or 4 students to form a group, and we give explicit instructions to each student. There's one task you have to focus on throughout this process. So the first student would be in charge of dropping beans onto maps. The student will be only one who handling the cup and dropping the beans. And well, different students have different ways to dropping beans, believe it or not. They actually face a lot of challenges about what's the most efficient way to keep all the beans on the same map so they'll jump everywhere. So they have all kinds of interesting issues while running this simulation. The second student would make the decision. Second student would be like the judge, decide whether a bean representing a student who is infected or not. The third student would be count beans and switch beans. We'll talk more details about that later. The fourth student will be the only one who's going to record data. So everyone have a very particular job assigned to them, and they will be, and it doesn't require high level of mathematical understanding. So no matter what's a comfortable level about mathematics, they can do a great job. So it's an easy place to start. And the process is we put 40 beans of one particular color into a cup. That's going to be representing 40 students who's susceptible. And initially, we decide 10% of this group of beans students are going to be infected. So we remove those 4 beans out of those 40 to be of one particular color from our cup, and we switch 4 other beans of the different cup in different color into our cup. And with this cup of 40 beans now of 2 different color, right? We first make sure we record that data. We start from 40 beans with 0, all of the same color, namely 0 infected students. Then we have 10% of them infected, so that's one color. 36 of those are not infected. So after we record our data, we begin to run our simulations. We toss the beans onto the dorm map or campus map. If a bean of color B, namely reinfected bean or infected students, fall into a particular room or building, then that location is going to be infectious that particular day. So any bean of a different color of the susceptible within the same building or the same room would be infected. So we let the student judge to make the decision whether being of a color A, touching a being of color B, touching each other in the hallway or in the outdoor region. Outdoor region would still be considered infected or not. So we have a judge to make consistent decisions throughout the process. And then once we decide some of beings are infected, then we switch their color to reduce the number of susceptible students, increase the number of infected students. So for example, if we have 2 newly infected beings, we switch it from color A to color B, and we put the 40 beings back into the cup again, getting ready for our next round. But of course, we should always record the data. So we update our table a little bit. The yellow table, yellow cells are the new data, 2 more infected. So changing infections 2, therefore susceptible count becomes 34 and the infected count becomes 6. And we repeat this process over and over again until there are no susceptible count anymore, so we can fill in our table. The process is relatively straightforward, and every student get a chance to contribute and have nice discussions. And then what we move to next is we try to process our data. We do have a empty space cell in the fourth row. So first of all, we fill in 0 for that row, which is no more changing infection. And then we calculate, fill in the number of infections for every 2 days, which is the extra row we have, the number of infections every 2 days. Well, part of the reason we want to do this is we want to improve. We do understand changing infection is a rough estimation of the derivative. We want to improve our calculation just a little bit. So that's why we are taking average of the current and the previous change in the infected value to help us to calculate the infected rates a little bit later. That's why I'm taking the number of infection every 2 days and do the calculation filling this whole row. I do want to mention before day 0, there's no infection ahead of time. So that's why I'm adding 0 to the 2 to calculate the infection average out on the first day. So after we did this calculation, the last part is pretty straightforward. We calculate and fill in the last row, which is the infected derivative. We are averaging out 2 days, so every single thing we filled in should be the previous column divided by 2. So we can get the answer pretty straightforward. Now all data are collected. We're going to try to sketch the graph. Again, every student will be charged of sketching one graph. What I did in class, students plot everything on a piece of paper, but later I figured out it might be a good idea to plot it on decimals and let each student plot just one set of data. We're going to begin with give them short instructions how to use decimals. Some engineering students are super good with it. Some students have never heard of it before, so they do see a little bit challenge of using this. So this is what I prepared to use next time I teach this course. My student did everything on paper. So we're gonna plot the graph number 1, susceptible count versus time. So they get a chance to learn how to put everything into decimals, into a table, and plot it on the curve, using the lines to connect everything together. So we'll see a nice graph, and use a range to modify the range of X and Y axis to make sure they are showing the right graph. Everything lies in the center. So once students get a chance to plot the susceptible count and the infected count over time, which are 2 easy starting points, I ask them to discuss how they think the number of susceptibles and infected should be changing and explained in plain language, and then describe the observation they have from the graph, see if it matches with their conceptual understanding. So they kind of connect the real life situation they think should be happening with the data they collected, which gives them a chance to practice on describing mathematical observations and translate it into plain language. Well, the interesting part, of course, is the next 2 graphs. The next graph, we ask students to do infected derivative as a function of time. We ask students to describe the observations from this graph and ask students to decide whether the 2 functions, which one would be a nice one to mimic the behavior in the graph they plotted. And of course, it's very, very abstract. That's why we say, okay, I ask you to plot the graph of A times sine t, our model number 1, and A times t minus b times t minus c in decimals on top of the data they collected, so they can compare the visualization of the model, which may or may not be a good model, over their data, see how that works. Again, like I said, decimals should work nicely, but students had some struggling when I just directly threw them under the bus, say use decimals. So I added those extra demonstrations saying you can have a slide bar, which gives you a chance to change the parameter during the process. You'll be able to change the range of the parameter. You can slide the bar to change the parameter on your graph so you can see the differences in action. And then you can also click on the play button to let the parameters change automatically, so you can visualize how your graphs, the curves from your model are changing, and how does it match with your data. So by doing this, they would hopefully find a way to see which model might work better and how closely we can match it with our data, and they can find the parameter at the same time, which is usually a big struggle. We try to reduce the amount of calculation in this process. So slide the bar, use decimals to be part of the discussion is quite helpful. And of course, we do the same procedure again, plotting the graph of the infected derivative over the number of infected count. I mean, we all know the answer. The best model is dy over dt. The rate of change of infection is some kind of constant times the newly infected multiplied by 40 minus y, which is how many people are left to be infected. We all know this answer, but this is extremely challenging for students to capture. Part of the reason is that they don't feel too comfortable about describing a function without the independent variable in it. In other words, implicit function. So I encounter a lot of pushback and struggle when we move on to discuss those two components. All students feel extremely comfortable and focus a lot on this previous discussion. They really enjoyed it and everything worked out nicely, but they struggled with the new discussion when we don't have the time to directly appear in our model. So that's why I added those slide bar and put decimals as part of this procedure. So hopefully student will find this easier to understand next time I run it in class, which is going to be at a first day of our D class again next semester. So once we did this, what we try to do is students know the parameters already. They have some general feeling among A, B, C, D, which might be a good model to describe the phenomenon. So I tell them to now go to Symbol Lab and use Symbol Lab to solve the differential equation for you. And you have the parameters. I mean, you could keep your abstract parameters if you want as ABC, but also you had some parameter information from the decimal simulation. So you have a nice set. So based on the solution you found with the help of Symbol Lab, what do you think would be the long-term behavior of the number of infected population? What's Y is going to be like? Well, T approaches infinity. This is some kind of discussion we have from Calculus 1. So all students hopefully would feel comfortable to provide some more discussion about this. And then we sit together, we report back about their, what do they believe? We vote on which is the best model and discuss about that. And we do some analysis afterwards. The analysis include compare data with a model with another group. Do you see similar results? If not, what do you believe lead to the differences? Did you drop the bean the same way? Do you make the criteria the same way? Can our simulation be used to study disease with a quick recovery? Can our simulation be used to study a disease that lead to a very quick death? And what are some other live cases that this simulation can or cannot mimic? And how can we improve our simulation based on the particular situation you want to describe in real life? And how does that lead to a modification of our model? So like I said, there are some very interesting struggles in the class. Students have difficulty making the beans to fall on the map. So it took a long time for them to figure out what's the most efficient way to do this. And some students find it hard to follow the instructions because we don't have the computational part of it. They have difficulty plotting the graph and match it with model. And like I said, model 3 and model 4 are harder to understand because they are implicit functions. People feel less comfortable about using decimals without my detailed instruction, which I didn't aware as a challenge earlier was also a struggle. And well, other challenges are lose track of group members. We did this everything the first day of class, and we finished discussion and everything, but students are instructed to have some other discussion, write down their reports and turn everything back in the second class. My students lose track of their group members, and their students drop the class after the first day, so they can't finish the project. And for example, data are ugly, and a lot of discussion actually happened in the class where students talking about the ethics of, should we try to do our best to get as many students infected, as many beings changing the color, or should not? And that actually get them super excited. So there are some interesting variations that can be easily implemented. For example, I mentioned, what about vaccination and recovery, right? What if some people just gonna be removed from the infected group very quickly? So we can have a third color, and then we can have people who get quarantined if it's COVID, they're gonna be removed from this population of 40 students. Or we can have different initial conditions, we can have different size of beings and different size of the maps, right? And what about adding this exposure part into the simulation? So they are not contagious, but the student developed symptoms already. Well, we have a lot of colors of beings and MM, so it's nice to include this extra modifications. And how about on-campus public events, which bring in immigration and bring extra infected population during the process? And repetition is a charm. We're gonna repeat this several times. We repeated already in class when we introduced Euler's method, and we're gonna repeat it several times when we move on to systems of differential equations. And I try to do modeling focused discussion at least once a month, and a student would be expected to write a final report. And towards the end of the semester, what they write should have multiple parts. They should have analytic calculation of the simplest model, solve it by as a separable equation. They should provide numeric simulations of the system of nonlinear model with a complete SIR model. They should provide explanation in plain language, and they should write a short action instructional summary to a politician, namely there should be no math in it. People should understand it easily without math background. So quick summary, I have 24 students, it's a 75 minutes class. Everything lasts about 60 minutes or so when we try to run a full model, full simulation. I did assign groups. I did begin with instructions, but I'm not sure how to grade the first part of it. Students seems to be highly engaged and happy about this, but I don't know, I will get a chance to, towards the end of the semester, I will see their final report and see how things works out. This is based on the common code spread from Semio course material. I hope everybody get a chance to explore more materials on that web page. And that's all the time I have. Any questions, suggestions, and comments?
I'm going to jump right into your title, which was that you do this on the first day of class. I took an educational psychology class in college where we learned that it's the very first things that you tell as a person, whether it be in a class or anything else, that they remember. So the last thing that a professor should do is to waste that first day going over the syllabus. That's fertile ground. And so I'm totally on board. You want to do something like this. I do something similar. I do Newton's law of cooling, and I bring a hot pot to class, and we actually do the calculations, and then we take a couple of measurements, and then we can predict over that whole class period exactly what the hot pot's going to be doing, and they get it within a degree after every 10 minutes or so. And it's really neat to have them enthused about the whole idea after the very first day of class already. So that's good pedagogy.
Thank you. Yeah, I really enjoyed that. And I was nervous about skipping introduction and everything, but still get to know each other very well. I think the general feeling in the class, because they engage with so much with each other on the first day, so they become friends very easily and very quickly. So that's also nice.
Any last minute questions for Yanping?
I'll just do one more follow-up. A colleague gave a talk once, enthuse them or lose them. He gives that to all incoming professors, saying that first day of class is so important. My own graduate advisor at Iowa State said the two most important days of class are the first day and the day after the first test. And I totally agree that those are critical days for capturing your class. So think carefully about how you want to use that time.
Yeah, and just one very short to add to what you just said. I think one thing we could at least do is don't cut the first class short. We should use all the time. Don't let them go early. That's the easiest thing to do, I think.
Give them a long assignment.
Yep.
I just want to mention, I did a group work on my first day of class, and I had to tell the students class was over when it was like 5 minutes after class ended. So,
Oh, that's nice.
yes.
Then you have to keep doing that every day. Like,
It's okay. I don't mind that.
Did a lot, you said they had difficulty keeping them all and making a decision on how to toss them out. I mean, it's amazing how practical things like that bother them and they go on the floor and everything, you know?
Yeah, I never thought about it, because when I did with the semioid workshop, I put it on my table. I'm so close. Everything was easy to manage. I have students putting the map on the floor. They stand up and they drop the bean. And later they find out, okay, that's not a good idea.
Well, thank you very much, Yanping. For those of you who are in the room now, you ought to know that Yanping and Lee are the people responsible for this conference. Yanping is the one who's been building our Gather and dealing with Gathered. It's a brand new platform for this conference. The last 2 times we had it, whoever we contracted did everything. And this time we do everything through Yanping and Lee is here for what happens on the moment or before the moment, anticipating. So